After studying this module, you shall be able to compute charge on the ionic cloud surrounding the reference ion or the central ion, understand the distribution of charge on the ion atmosphere in the space around the central ion, learn the contribution of ionic cloud to the electrostatic potential psi r, learn the physical significance of Debye-Hückel length chi inverse. In the Debye-Hückel model of dilute electrolytic solution, an arbitrary chosen reference ion is considered to be situated at the origin of the spherical coordinate system. This reference ion is surrounded by the smoothed out charge of the other ions. There exist local inequalities in the concentration of the positive and negative ions, due to which the smoothed out charge of one sign does not cancel out the smoothed out charges of the opposite sign. Therefore, as a result, there is an excess of local charge density of one sign. Thus, the principal objective of the Debye-Hückel theory is to calculate the time average spatial distribution of the excess charge density around a reference ion. In this module, this objective will be attained. The relation between the electrostatic potential at a distance r from the reference or central ion to the charge density psi r at a distance r is given by the Poisson equation. This has been shown in figure where an infinitesimal volume element dV at a distance r from the reference ion, the excess charge density rho r and the electrostatic potential psi r. Mathematically, the Poisson equation can be written as given by equation 1 as 1 by r square d by dr of r square d psi r by dr is equal to minus 4 pi by epsilon rho r. In the previous module, we have also derived the linearized Poisson-Boltzmann equation, which is given as equation 2. This can be written as equation 2a, where chi square is equal to 4 pi by epsilon k t summation n I naught z I square E naught square. We have also obtained the appropriate solution of linearized Poisson-Boltzmann equation as given by equation 3. The linear relation between excess charge density rho r and potential psi r can be derived using Poisson equation 1 and linearized Poisson-Boltzmann equation 2a. Thus, we have the equation 4 as substitute equation 3 in equation 4, we get equation 5 as due to unequal distribution of positive and negative ions, there exists excess charge density. Therefore, equation 5 describes the distribution of ions around a reference or sample ion. In order to understand this distribution of ions, we need to understand the physical significance of equation 5. The arbitrary chosen central reference ion is surrounded by a cloud or atmosphere of excess charge. This is shown in figure which shows the distribution of excess charge density around a central ion can be visualized as a cloud or atmosphere of net charge around the central ion. This ionic cloud extends into the solution, that is, the distance r increases. The variation of excess charge density as a function of distance r from the central ions occurs in an exponential way. This has been depicted in figure 3, shows the variation of excess charge density rho as a function of distance from the central ion. The sign of the excess charge on the ionic cloud is opposite to that of the central ion. Therefore, either a positively reference ion has negatively charged ion atmosphere, or a negatively charged reference ion will have a positively charged ion atmosphere. This is depicted in figure which shows a negatively charged ion is surrounded by a positively charged ionic cloud and vice versa. We have discussed the charge density at a given distance, but we need to compute the total excess charge contained in the ion atmosphere which surrounds the central ion. Therefore, we consider a spherical shell of thickness dr at a distance r from the origin, that is, from the center of the reference ion. This is depicted in figure which shows a spherical shell of thickness dr at a distance r from the center of the reference ion. The charge of dq in this thin shell is equal to the charge density ρ times the volume of the shell, that is 4 pi r square dr. That is, dq is equal to ρr into 4 pi r square dr. This is our equation 6. The total charge in the ion atmosphere, that is Q cloud, is obtained by summing the charges dq contained in all the infinitesimally thick spherical shells. In other words, the total excess charge surrounding the reference ion or the central ion is computed by integrating the charge dq in the thin shell, which is a function of the distance or from the central ion. The lower limit of this integration corresponds to the distance from the central ion at the point ionic cloud is considered to start, while the upper limit is the point where the ionic cloud ends. We know that the ionic atmosphere begins at the surface of the ion. Therefore, the lower limit of the integration depends on the model of the ion. Thus, the model chosen by Debye Hückel was that of point charge ions. In this model, the lower limit is r equals to 0, while the upper limit is r tending to infinity. We have chosen the upper limit to the infinity because the charge of the ionic cloud dq undergoes an exponential decay into the solution, and it becomes 0 only in the limit when r tends to infinity. Thus, we have equation 7 as substituting equation 6 in equation 7, we get equation 8 as substituting equation 5 in equation 8, we get equation 9 as. This can be simplified into equation 10 as. The integration of equation 10 is done by parts, thus giving us the result as written in equation 11 as Q cloud is equals to minus Zi E naught. Equation 11 shows that a central ion of charge plus Zi E naught is enveloped by a cloud containing a total charge of minus Zi E naught. This has been shown in figures which depicts the total charge minus Zi E naught on the ionic cloud is just equal and opposite to that of plus Zi E naught on the central ion. Thus, the total charge on the surrounding cloud is just equal and opposite to that on the reference ion or the central ion, which also explains the electroneutrality for the ionic solution as a whole. Hence, central ion or reference ion together with this cloud has a 0 net charge. Now, we shall see the distribution of charge of ion atmosphere in space around the central ion. The net charge in a spherical shell of thickness dr at a distance r from the origin is given by equation 5 and 6 is given by equation 12 as. Thus, the excess charge on a spherical shell varies with distance r and has a maximum value for the given value of r, which is given by equation 13 as dq by dr is equal to 0, which is equal to d by dr of minus Zi E naught e to the power minus chi r into chi square into r. This is from equation 12. This can be further simplified as we get equation 14. Since the term Zi E naught chi square is finite, therefore, in order to satisfy the condition of equation 13, we have equation 15 as 0 is equal to e to the power minus chi r minus r times chi times e to the power minus chi r, or e to the power minus chi r is equal to r into chi into e to the power minus chi r, or r is equals to 1 by chi, or we get equation 16 as r equals to chi inverse. Hence, the maximum value of the charge contained in a spherical shell is attained only when the spherical shell is at a distance r equals to chi inverse. Therefore, chi inverse is known as the thickness or the radius of the ion cloud which surrounds a reference or central ion, where chi inverse is given by equation 16 as, or chi can be given by equation 17 as, which means chi inverse is equal to as given by equation 18. An elementary dimensional analysis of equation 18 reveals that chi inverse has the dimension of length. It can be proved as follows. Dielectric constant epsilon has the units of Coulomb square, Joule inverse, meter inverse. Boltzmann constant K has units of joules into Kelvin inverse. Temperature is expressed in Kelvin. Ni naught, that is the number of ions per unit volume, is given by meter cube inverse. Zi into E naught, that is the charge, is expressed in coulombs. Thus, from equation 18 we get, therefore, chi inverse can be expressed in meters as given in equation 19. Chi inverse is also referred as Debye Hückel reciprocal length. Now, we shall see the calculation of the contribution of the ionic cloud to the electrostatic potential psi r. The effect of ionic clouds can be understood prominently by considering a thought experiment in which the charge on the ion cloud does not exist. Therefore, there is only one charge now, that is on the central ion. The potential at a distance r from the central ion can be given by the similar formula for the potential at a distance r from a single charge. Mathematically, this can be expressed as psi r equal to Zi E naught by epsilon r. This is our equation 20. Now, let the charge on the ionic cloud be switched on. Then, the potential psi r at the distance r from the central reference ion is not given by the central ion alone, but is given by the law of superposition of potential. That is, the potential at distance r from central ion psi r is the sum of the potential due to the central ion and that due to the ionic cloud. That is, psi r is equal to psi ion plus psi cloud. This is our equation 21. Thus, the contribution of psi ionic cloud can be easily found by rearranging equation 21. We get psi ionic cloud is equal to psi r minus psi ion. This is treated as equation 22. Substituting equation 20 and 3 in equation 22, we get, or this can be simplified as equation 23 as, the value of psi as seen from equation 6 and 17 is proportional to summation Ni naught Zi square E naught square. Thus, in sufficiently dilute solutions, summation Ni naught Zi square E naught square can be taken as sufficiently small in order to make chi less than 1. Therefore, from equation 23 we get, or this can be written as equation 24, or this can be written as equation 25. Using equation 20 and 25 in equation 21, we get equation 26 as, the second term in equation 26 arises from the ionic cloud. Therefore, it reduces the value of potential to a value less than if there were no cloud. Equation 25 also leads to another way of looking at the quantity chi inverse, that is the Debye-Hückel reciprocal length. Since the ionic cloud potential psi ionic cloud is independent of R, therefore the contribution of the cloud to the potential at the site of point charge central ion can be considered to be given by equation 26. Also, if the entire charge of the ion atmosphere were placed at a distance chi inverse from the central ion, then the potential produced at the reference ion would be minus Zi E naught by epsilon chi inverse. Therefore, the effect of the ionic cloud, psi ionic cloud, is equivalent to that of a single charge equal in magnitude but opposite in sign to that of the central ion placed at a distance chi inverse from the reference ion. This has been depicted in figure. Thus, this is also the reason that the quantity chi inverse is known as the effective thickness or radius of the ion atmosphere surrounding a central ion. Now, we shall see the effect of concentration on the thickness of ionic cloud. We have seen from equation 6 the relation of chi square is given by, since all the terms in equation 6 are constant, therefore chi inverse is also a constant for a given solution. Dilution of a solution decreases Ni naught, that is the total number of density of the bulk or the number of ions for unit solution. Thus, from equation 6, chi square also decreases, which implies an increase in chi inverse. We have already learned that chi inverse is known as the thickness of ionic cloud. Therefore, on dilution, the thickness of the cloud increases. In other words, on dilution, the cloud becomes more and more diffused, or on increasing the concentration of the solution, the ionic cloud becomes concentrated on reference ion. Now, we shall summarize what we have learned in this module. The local excess charge density around the reference ion is given as the total excess charge contained in ionic atmosphere which surrounds the central ion is given by Q cloud is equals to minus Zi E naught. Chi inverse, that is the Debye-Hückel length, is the measure of the thickness of ionic cloud. This is given by the potential of the ionic cloud surrounding the reference ion is given as psi ionic cloud equal to minus Zi E naught divided by epsilon chi inverse.